The broadcast is now starting. All attendees are in listen-only mode.
Well, hello everyone. It is the top of the hour, and depending upon where you are in the world, I'd like to say good morning, good afternoon, or good evening. My name is Eric Camuli. I'm the Customer Success Officer here at SevenSignal, and it's my pleasure to be your moderator today. And we have got just a jam-packed session for you. It's going to be really exciting. And we're joined by Keith Parsons in our webinar today called Tips, Techniques, and Tools for Troubleshooting Wireless LAN. So very excited to have Keith with us today. And also Jim Vada, who is our Director of Global Wi-Fi Solutions here at SevenSignal, and he'll be helping out a little bit as well. Now, what I'd like to do is just take the first 3 or 4 minutes of our time together to just give you a background of SevenSignal, just tell you who we are and what we do. And then I'm going to hand it on over to Keith, who's going to get into all of the meats and potatoes that we're expecting today. And we will have a question and answer session at the end that Jim will be assisting with. If you have questions, I would invite you to use the question box in your control panel. Put those questions in there. I will be reviewing them. And then when we get to the end of our presentation, I will do my best in order to get all of those answered for you in working with our panel today. So thank you very much for that, and let's get started. I first want to tell you a little bit about SevenSignal if you don't already know. We were established in 2007 in Helsinki, Finland by a couple of Nokia engineers who saw the future and how Wi-Fi was really going to take off. We relocated to Northeast Ohio, the Cleveland area, in 2013. And believe it or not, there was an abundance of Wi-Fi talent in this area, Akron, Ohio being the home of Aeronet, which was acquired by Cisco back in 1999, year 2000, and also Telzon, which was eventually acquired by Symbol. So really quite remarkable how we lucked into that. So here at SevenSignal, what's most important to us is the Wi-Fi experience, and all of our products are really geared towards trying to monitor and measure the Wi-Fi experience from your point of view, your device's point of view, and then use all of our analytics in order to identify root causes. So let me just tell you a little bit about our platform. It really is quite comprehensive. We've included all elements of Wi-Fi, from the device to what's going on in the air to what's happening with access points, and also what's happening even on your network. It really takes all 4 of those legs in order to stand up high quality Wi-Fi network, and we're going to learn a little bit more about that today. So it is a kind of a one-stop shop. Let me just tell you what our products are really quick. So on the right side of your screen, we have a unit that we created. It's called the Sapphire Eye. And we refer to it as a high performance client because it will assign to your SSIDs, it will attach to the radio, we give it credentials so that it will authenticate to your network. It has to go through DHCP services in order to get an IP address. So we're testing and monitoring all of that in terms of a Wi-Fi experience standpoint. And then once on the network, we're going to perform a series of transactions. We're going to be measuring throughput, packet loss, latency, and jitter, even calculating a MOS score for voice quality 24 hours a day, and reporting back to you if the Wi-Fi experience is declining in some way, shape, or form. Now, in addition to that, the Sapphire Eye is also a Wi-Fi sensor. So 24 hours a day, it's measuring airtime utilization, beacon availability. There's a built-in spectrum analyzer, and so we're seeing what's going on in the air from an RF standpoint 24 hours a day, and storing all of that data in the cloud for you for 90 days, which is really nice when you can look back in time as to what was happening in the air at a certain time and certain place. Now on the other side over here on the left, we have Mobile Eye. Now Mobile Eye is software that will go on your device. So it's going to reside, for instance, on my laptop computer right now. And it runs as a service in the background. And again, all the while that I am on a Wi-Fi network, it's doing 3 things. One is it's gathering up all of my connection information. So I can see what access point I'm on, what network I'm on, what my signal strength is, what my data rate is. It's also performing throughput, packet loss, latency, and jitter tests, so I can actually see my experience. And then also it's gathering up the configuration of my laptop so that I can now create reports that tell me which devices with which adapter driver combinations perform the best or the worst on my network. And so this completes the cycle. It's a total package in order to assist with basically everything you need to know in order to find and fix Wi-Fi issues, troubleshoot complaints very quickly, and not only that, but also be proactive in identifying before the phone rings, before people get upset with what's happening. So that's it. That's all I wanted to tell you guys. We are going to have a regional users group in Nashville right before Wi-Fi Trek. So if you haven't signed up for that, please go to the URL that you see on the screen, go.sevensignal.com/rug. That's what we're going to do in Nashville. We're going to cut a rug. And we're also going to be in Prague with Keith at his Wireless LAN Professionals Conference on October 7th. So that should be exciting as well. And with that, I'm actually going to change hand the reins over to Keith Parsons, and I'm going to allow him the opportunity to tell you a little bit about himself, and also just take it away, Keith.
I need to do that mute thing or you can't hear what I'm saying. So welcome. Yeah, so this is the topic we have today is on how to troubleshoot. And first, little bit about me. I do, oh, sorry, I gotta get my mouse in the right control. I do wireless. So I run a company called Wireless LAN Professionals. I kind of collect certifications. So every year I try to get, I don't know, 4 or 5. This year I think I might get 7 more. It's just kind of a thing I do. Been doing design and troubleshooting LANs for a long time. And this year started to work on a troubleshooting course. For 12 years I taught a troubleshooting course using Air Magnet, and it was well received, but it's been years and things have changed and we were updated, so I decided to update a bit. Anyway, this is where I live when I look out my backyard. Not right now, the snow is gone, it's summertime. Actually, there's still a little bit of glacier on top. And this is my hobby, is staying with my, well, there's 10 of my 11 grandkids, so it's kind of fun. We just had them all together a week ago at the lake. So into the troubleshooting. So we're gonna start here with just the troubleshooting process from identify, recreate, locate, solve, document, verify, all these little steps. And this is standard for wired networks for troubleshooting just about anything you want to troubleshoot, and we're going to skip it because what we want is something specific for wireless. Well, to start, I want to recommend a book for you. It's called The Goal. Eli Goldratt wrote it a long time ago. I mean, I'm old and I read it when I was in university, then I read it again when I was in MBA school, and it's about how to find bottlenecks in whatever system you're doing. Now, it's specifically for manufacturing or retail, whatever, but we can apply the same idea of we fix problems by finding the bottleneck. Now, in many of our networks, and I started in the server world, on the left side, when we had a server problem, we could mask, maybe not find the bottleneck, but we could mask the bottleneck by just throwing more RAM at it. You just kept throwing more and more RAM, and wherever the bottleneck might have been, it could have been in the hard disk controller, could have been the drive head speed, could have been all sorts of places, but you can hide it. In the WAN on the right side, we can hide WAN problems by just getting bigger and bigger pipes. And so there's some ways we can mask bottlenecks, but in wireless, there is no real easy way, because the thing what we need in wireless is more air times. And we have kind of a limited supply that the FCC has allowed us to use. So we don't have this quick, easy, let's just throw something at it to make it go away. The problem is a lot of people in the networking industry think that adding an access point will fix it. Well, if we were in a wired network and we had, you know, we didn't have enough ports on our switches, you can just add another switch. That doesn't work though when we're in the wireless world. So the first step here is I'm going to go back in time. This is back to 2016, and Lee Badman, Mr. Wired Knot, He labeled this the soon-to-be famous cocktail napkin Wi-Fi big picture. I loved it. As soon as I saved it and I kept it, and I actually printed it out and stuck it on my wall. It was a way that he used to look at his wireless problems and figure out, are they really wireless or are they someplace else? The little black boxes are things, the red stuff are things that might have gone wrong, and it was a good start. And sorry it took me so long to get this famous for you, Lee, but your picture is now being shared around the world. But here's our problem. Occam's razor. William of Occam was a priest back like forever ago, 1300 or something, and he stated, well, he stated in Latin, but this is the translation: more things should not be used than are necessary. Now we've thrown Occam's razor at a whole bunch of other problems, saying the simplest answer is probably the best, and I like using that on many things. But on the right side, we have a little cartoon joke. Simple but wrong is where most people go. Complex and right. And sad to say, what we're doing in wireless is too many people look to the left rather than to the right, because it's easy. If you have a problem on your Wi-Fi, that's a Wi-Fi problem. Add an AP, do something, change the power, choose, and depending on where you come from, if you're a controller guy, you think the controller can fix everything. If you're a survey guy, you think, oh, I just need to do another validation survey and then I can find it. Depending on where you come from, you have a whole different point of view. But what I want to do is take Lee's original piece and find out what's all of the complexity that's in wireless, which leads us to this picture. So here's potential issues in wireless LANs. Any one of these could cause an end user to say, Wi-Fi sucks, Wi-Fi slow, I don't like Wi-Fi, what's wrong with your Wi-Fi? Now, any one of these bubbles, and there happens to be 36 different bubbles, 37 of them, plus a big red box around RF medium, any one of them will look like a wireless problem on a wireless client. So just because a complaint comes in and says, oh, this is a wireless problem, doesn't mean it's necessarily a wireless problem. And then for every one of the bubbles, we went through and said, what are some things that could go wrong with that specific thing? Now also note, around some of the bubbles, there's little circles, little arrows going around. That means these are processes that flow. So the contention process in the upper left corner in the RF medium box, the contention process happens for every single transmission that happens in RF medium. There's a process defined called DFS, which is kind of silly because the distributed function of it is that it's not, sorry, DCF, distributed coordinated function. The coordination actually isn't coordinated. It's just the protocol is doing it itself. Or the MCS process, frame by frame, every transmitter decides how it's going to package the bits it wants to send, what kind of modulation, what kind of coding, what kind of channel width, whether or not the guard interval is on, all before they transmit each individual frame. The overhead, there is a massive amount of overhead in 802.11, and it's just kind of hanging out there in this bubble in a box just as a placeholder, so when we get there we realize we're not going to get what we expect. And the DFS process, APs are going every time they're out listening on the frequency, they have to know whether or not they're on a DFS channel and what should they do if they see someone else and how they get all their clients to move along with them. So just the RF medium has a bunch of pieces. So for each one of those, we made a little list, and this list has over 400 items of individual things you might have to look at if you're trying to troubleshoot wireless. Any one of them could be wrong, could be broken, could be slow, could be not doing what you expected, could be misconfigured. So yeah, if we go back a little bit, we're on the complex side. This isn't an Occam's razor situation, though we would like it to be. It's really complex. So what we need is tools to see things. I read a book by Adam Savage a little while ago called Every Tool is a Hammer. And it's kind of backwards of the joke that people have said. If you have only a hammer, all the world looks like a nail. And so I see this all the time in wireless, people who think that the only tool they have is their controller, so they do all their work from the controller's point of view. Well, we need to have a tool that's going to do what we need and a specific tool to do specific things. So I took all of those items and all of the tools we could find and turned them into a little process. Now, this doesn't look like the process on the first slide I showed, because that was do 1, then 2, then 3, then 4, then 5, document, repeat. This is, yeah, the very core of it is we need to know what the requirements are. There's primary coverage requirements in RSSI, secondary coverage, SNR, data rates, density, capacity, LCMI, which is your client you're designing for. There's a whole bunch of requirements that are at the core of whatever we're doing when we troubleshoot wireless. So if you don't know what your requirements are, it's really, really hard to troubleshoot them. Now, I also made this kind of loops as they go around, because different sets of tools give you different sets of information, but there is no flow. There is no one way to go about it. So on the left side, there's an interrogate bubble, kind of the dark red, and it's using packet capture. So if you are Peter McKenzie and you are a guru at packet capture, that's his first tool. He walks on site, opens up his OmniPeak and starts capturing, and that's how he sees the world. I'm a validate guy myself. I show up at my customer site to troubleshoot, and the first thing I do is whip out my Akahau Pro and survey the place to make sure the RF is meeting the primary, secondary, SNR, data rates, density, all those requirements, so I know that it's not an RF problem. But if all you have is a Wi-Fi scanner with you, Wi-Fi Explorer Pro from Adrian on your Mac, you can turn that on and run that way. Or in the upper left-hand corner is the managed corner, and this is where SevenSignal fits in. If you have a SevenSignal solution, either with a Sapphire Eye or with Mobile Eye, you can use that to look and start your process of troubleshooting. Any one of these is a good place to start. You may be able to solve the problem just in one of the loops. You may have to move from one loop to another loop. Measure is using things like iPerf to do tests. Some third-party solutions like SevenSignal allow you to do perf testing directly through and do synthetic testing on your network from the Sapphire Eye. So we looked at what the troubleshooting causes were and the 400 plus things that could go wrong, and let's talk about some of these tools. Well, before we get into the tools, let's talk about the picture, the big picture. And we're going to break this down into little chunks. By the way, in this little 45 minutes we're going to spend together, we're not going to teach you how to solve anything. But what we will do is show you how to use a framework to find what the problems are. So we're going to start with the RF medium box. So in the RF medium box, it's the RF medium itself. And there's a list on the right side. I'm not going to go through all the list, but these are all the things that you might want to look at inside RF medium that may or may not be causing the issue. Any one of them could cause someone to make a complaint. If there's a complaint and the problem is in RF medium, there's a certain process and certain tools we're going to use to go through and figure that out. Now, one of these boxes, one of the bubbles inside this box is a contention process. The contention process is how clients, APs, devices, anything that's going to access the RF medium using 802.11 protocol, it's going to go through and say, is it my turn to talk? Now, there's a distributed coordinated function that allows all devices to share the medium, but they do it by having random back-off timers. They do it by waiting before anyone talks, because there is no they listen before talk, but there is no ability to know there's a collision detection. So we have to have this very complex process, which, by the way, takes time, dead air, basically, of no one transmitting in order to trigger the result that someone could transmit. So for every single transmission that goes in the air, there's this contention process. And by the way, I don't know of any tools, because this happens inside the firmware, down at the chip level of a client. We can kind of guess what this is from the outside, but I don't have any tools that will actually allow me to say what was my last CW on the transmission I just did. So contention process is one of the bubbles, and it could be the cause of why we're having issues. You need to know how this works, what are the symptoms, and how you can fix it. The next one is the MCS bubble, and you can see this in the upper right-hand corner. Depending on our signal strength, if we have low SNR, we're going to use a less complex modulation. Less complex modulations means we're going to transmit at a lower data rate. Because I use a lower data rate, it takes more time. So lower SNR means I have slower network, lower utilization, which also means I'm not getting the density I needed. To get density, I need to talk fast. To talk fast, I have to have high SNR. But the flip side of high SNR is if I talk loud, you see my S as your N. And so whenever you have two or more APs on the same channel in the same area, you have the capacity of one because they're sharing that. That's the big killer in Wi-Fi. Not everyone knows that Wi-Fi is 100 times, 20 dB, more sensitive to other Wi-Fi than not Wi-Fi. So sometimes when we think about things, people say, oh yeah, it's a microwave oven. Yeah, actually we're 100 times more sensitive to other Wi-Fi than we would be to a microwave oven. Now the decision to choose an MCS, and that's the table on the next chart, to choose an MCS is started during the association process. An AP and a client negotiate and say, I can do this, you can do that, and they get a subset of what they both can do. And because they have some subset, when it's time to actually talk, when the AP talks to the client, it uses a portion of the subset. When the client talks up to the AP, it does. Those do not match, nor should they. I mean, it'd be nice if they could, but rarely is that going to happen. Each transmitter is making his own decision. So one of the health checks we come across inside Wi-Fi is checking what the data rate is or what the MCS is, because per frame, every device that transmits is telegraphing to the world, this is how healthy my RF is. Because if I have a poor RF environment, I'm going to automatically, every transmitter will automatically choose the best possible transmission technique. What type of modulation, what type of coding, what type of guard interval, and what spatial stream, as well as what size channel, which gives you all these little options on the screen. So all we have to do to find out if a device, either an AP or a client, is having trouble with their wireless is to look at their MCS and find out they're self-reporting. They're saying, hello, I'm diagnosing myself because I couldn't do 866, so I slowed down to 650. I couldn't do 650, so I slowed down to 90. I couldn't do 90, so I went to 6.5. There's all of these choices, and vendors all make this very proprietary, how they choose to make those decisions. So that's all about the RF medium. Well, what about if we go to say, how does a client actually even get on a network? A lot of the issues that we could be troubleshooting are, how do clients join? Well, if we first have the end user, and there's a whole list of issues that the end user could do. The device itself could have issues. It could have problems with its drivers, its firmware, how it was programmed. And then we get to the association process. And at the end of association process, a client will choose to either go on and hit open or pre-shared key or radius. They'll either have no encryption or TKIP or AES, and the control port will be open or not. And in the end, you'll get connected and have upper layers. So we can use the knowledge of how this flow works as a telltale sign in our troubleshooting, that if I get an IP address on my wireless NIC, I must have gone through these processes. We can't always see the flow. If we have a packet capture tool, we probably can, but we can do a quick test to just say, is an IP address, do I get an upper layer? And if so, then I know that the pieces before it work. Now I've been calling this process of association the green diamond for nearly 20 years. Now that was because I had this really old graphic. This graphic's been around, I've been using it for at least 19 years. And my graphic artist who did it, I said, we just need to make the laptop, which you can see as a PCMCI PC card. So yeah, this is really old. But the process is clients send a probe request, they get a probe response, they make the decision, which is why the green diamond, the decision, is inside the client device. APs would like to influence that, but they actually don't make the decision, the clients do. It's green because we already used up the other colors. So yeah, for 19 years, we call this green diamond. It's a quick way of saying, what is that associating roaming algorithm? And on the right side is a whole list of bullet items, and this is in no way complete, of things that could go wrong during this association process. They're parts of the algorithm that would decide, why should I go to one AP versus a different AP? And the very last line on there is the things in 802.11k VNR, which the APs will try to influence the decision process. Which leads us to the big black on yellow in your face quote. This is changed up. I made it look this way because I wanted you to stop, think, and remember. Association is to wireless what a link light is to wired. If you had a link light on a computer, you plugged in an Ethernet cable into the port and you get a link light, do you troubleshoot up the stack or down the stack? Pause, think about it. Well, obviously, you're going to troubleshoot up because the link light's telling you it's working down there. Now, every now and then, it could be some rare thing that the cable's like missing one little bit and the link light worked, but the Ethernet cable's out. But for most of the time, if I get a link light, which then trips the TCP stack, which then goes and grabs a DHCP request for me, I know that the problem isn't in the connection at the physical layer, it's upper someplace else. We get the same thing with wireless. If I get through the association process, then I need to troubleshoot up the stack, not down the stack. So here's a review of what we just covered so far. 802.11 association, a minimum of beacons and then 6 additional frames. Then there's an authentication process, OpenPSK or .1x. Then there's an encryption process, either none or TKIP or AES. And then that opens up the port control, which allows us to go get upper layers. And then we can pass traffic on the local network, which then has a captive portal. So just looking at this one screen alone, you can troubleshoot and say, if I have a captive portal, I don't have a wireless problem. Because the only way to get a captive portal is to finish through all this. Now, it doesn't mean you don't have a problem. This doesn't mean the wireless is going fast. What it means is these processes took place so that I can then send data across the network. Well, when it comes to upper layers, we finish the VLAN assignment and get the DHCP request and IP address back in a subnet mask, a default gateway, and DNS. And the last step, one more time, the last step is a captive portal. So most of our users think that the captive portal was the first step, and they complain and think there's something wrong when you have a captive portal. Again, yeah, I'm an anti-captive portal kind of guy. Everyone knows that. But the reason is just getting one tells you that everything's working. Why are you punishing your users at that point? Now, if you notice in the upper right-hand corner, as I've been going through, the little bubbles have the little red circle because they're on the left side or the wireless side of our graphic. Well, this captive portal could exist, and this one shows it over on the green side. Because does it exist in internet? Does it exist on a controller? Is it on a separate server? Well, the captive portal itself has a huge amount of things that could go wrong. It has its own flow chart of how things work and issues that can happen, not to mention all of the other things that it could trigger along the way. Just troubleshooting captive portal alone is its own course on how to troubleshoot that. Well, another thing that we have to deal with in the RF, and so this I kind of jumped ahead to the captive portal being in green, but we see it and people complain about it on the wireless side. They'll realize it has nothing to do with wireless. If you are seeing a captive portal, if you're having captive portal issues, you don't have a wireless problem because you finished all of the wireless issues to even get here. So going back a little bit onto the wireless side, we've got a bunch of channels to choose from. Now in 2.4, we have 3. Sorry, we have 3. That's it. 1, 6, and 11, yeah, there's all sorts of ways you can break that down. But if you're running into 40 megahertz channels, you know there's a problem. You shouldn't use those in 2.4. If someone's on channel 4, yeah, we know they're going to have issues with ACI on channel 4. So I kind of skipped over the 2.4 issue because hopefully everyone's working in 5 gig. But in 5 gig, we also have issues. You can see on the 20 megahertz 40, 80 line that there is a different number of possible AP channels available from 25 down to 2. So if we go to 160 megahertz channels, ooh, we can go really fast at 160. We just can't do it because we don't have enough channel frequency. It's air times that we're trying to work through. And depending where you live in the world, there's different rules, there's different transmission rates. Whichever vendor equipment you're using should have these already hard-coded in so that if you pick and say I'm in country code Canada, all the rules get applied properly. Now, I added this screen just so you could see and visualize what it looks like. But the real issue here is, do we use 20s or 40s or 80s? And the answer is use the widest one you can until you can't. How do you know you can't? You can't when you get co-channel interference. So wider ones allow you to send data faster. That does not mean that they're better. That just means they allow you to send data faster. If I have 2 APs and they see each other on the same channel, I have the capacity of 1. So having the capacity of 1 80 megahertz AP, even though I have physically 2, isn't a good choice. Why don't I go to 2 APs, each with a 40, and they don't interfere with each other, and they can get higher throughput. Depending on your environment, you might be down to the 20 megahertz line. There are third parties out there, nothing in the enterprise space, that have 10 and 5 megahertz channels to get around that very issue. So one of the troubleshooting issues is look and see what you're using. Perhaps you're using the wrong one, which leads us from, we're still up in the red box about RF, and it leads us to talk about DFS. DFS just means that 802.11 isn't the primary user. There's a process that APs are going to go through to scan, to listen, to tell all their enables, send a channel switch announcement, get all the clients to move off. But the problem with DFS channels isn't just from the AP's position, it's that clients also have a harder time joining and roaming to these because they have to wait until they hear a beacon. Now, that doesn't sound like much to me because that's, I don't know, 1/10 of a second. Every AP is beaconing on a DFS channel every 1/10 of a second. But when I go to roam and a client's looking at it to say, oh, should I go scan the channels? And it takes me 1/10 of a second to wait before I even see something on a channel. And there's 20 channels or 16 that are in DFS, and I have to wait that long. That's a 1.5 seconds before I can even make a decision. And I might do it a couple times. Some vendors also don't scan DFS channels at the same frequency they scan non-DFS channels, which even slows down the roams even more. So DFS is great. I like DFS channels. I like using them. Just realize there could be some issues with respect to that. Another troubleshooting issue is if the DFS log events are telling you there's a bunch of DFS things, depending on your vendor, your DFS channels, those APs might move all to the same channel and overload a single channel. So you kind of need to know where that is in your environment. Now the next one, also up in the red box still, is what happens, and I just put the simple bubble called 802.11 overhead. These graphics I got from Aruba from one of their VRDs, but just a single frame. If you walk down the left side, this is the process that takes place to deliver a single frame. There's going to be AFES. It's a interframe space of just waiting time. So there's going to be an AFES that's going to say, depending on my WMM or access categories or QoS, whatever you want to call it, I have a different AFES amount of time, and that's just dead air. It's the trigger. And then there's a contention window, and the contention window, depending on my access category, could be 4, 7, 15 or higher. And then there's a BPSK preamble. All preambles are sent at the modulation of BPSK. And then there's an RTS, and then a CIFS, which is fixed time, and then a preamble, which is slow, and then a CTS, and then a CIFS, which is fixed time, and then another preamble, and then a high-speed preamble, and then a header, and then I finally deliver my payload. And of all the colors you see on the screen, the only thing that is actually giving us data throughput is the blue. Everything else is overhead. And so these screens are showing horizontal axes in time, and you can realize there is a lot of time that's totally wasted that's not going to be given back to us in actual raw throughput. So I went through this overhead thing just to, well, maybe scare you a little bit, but also let you know when you talk to your customers, when they say, I just bought my client should do 1.3 gig, and you don't net 1.3 gig, here's the reason. 802.11 is not at all efficient when it comes to be sending data. There's a whole bunch of steps that have to take place in order for that data to be delivered, and those overhead steps in time take a long time. It's also a reason why if you look and say, oh, I want to transmit this at 866, oh no, I slowed down to 650, you are actually, that's way below the threshold of the human can even sense, because most of that is the fixed amount of time that is taking place, not the actual overhead coming off of the blue that's being transmitted. So yeah, those all had to do with that little red box, the RF medium. Well, now we're going to move up a little bit, and here's the upper layers. We have to deal with all the issues in the upper layers as well. I mean, just because we're wireless doesn't mean we don't still use application impression session transport. Just a hint for those who want to have a mnemonic to remember this. What I like is from the bottom up, please do not trust salesperson's advice. Easy way to remember what the protocol stack is. So let's review where we did. We discovered the little red box, the RF medium, a couple of things there. We talked about the association process and how proprietary it is, and every client has a different algorithm. Their little green diamond is different, and that's different for a reason. The reason they're different is because they have different needs. If I'm Apple and I'm designing an Apple TV, I might want the stickiness variable to be very high because that Apple TV never moves from its position, so I don't want it to roam. But an iPhone would need to roam much faster, so we would have an algorithm that was used in the association process would be totally different depending on the device. Its decisions will be totally different. If I'm a barcode scanner and I'm in a warehouse, I actually don't want high-speed data, because high-speed data means that I need a lot more SNR, which means I need more APs. Well, I'm only sending 30, 40 bytes every time I pull the gun, so I would prefer a low data rate rather than a high data rate, and that is in the association process. Again, very unique. So let's move on, and we're going to move over to the right side now. All of these that are in blue also obviously could cause problems, but they're going to look like a wireless problem even though they're centered in the wired. So on the blue side, any one of these bubbles could have issues. Our wired medium, just the cable itself, could be wrong. Our ground could be off. The ground that the AP is using and the ground the switch using is off, which says even though I put in a gig Ethernet cable, that gig Ethernet and the Cat6 cable on one side work, but when I go to send data, it's going to slow down to 10 meg, maybe 100, because there's a differential in grounding. I have tagged ports versus untagged ports. I have a captive portal that's connected to my AP that may or may not be connected over to another captive portal somewhere else. QoS rides the entire thing. So this picture, any one of these bubbles could also have issues. So let's start at the bottom. Let's start with cable. When I first started in industry, I was using the silver satin stuff. This was what we used for telephones. None. There was no twists in the twisted pair. They were flat and straight. Then we moved on to twisted pair, and then we went to Cat 3, Cat 5, Cat 6. How do we take the same copper going the same distance at the same speed of light and make it go 1,000 times faster? Now, one was we changed the protocols. We used the same copper, the same speed, but we did a lot of things to lower interference. We lowered crosstalk, both near side and far side crosstalk, by doing different things with the twists. We had the twists with the same ratio. We changed the twist ratio. We added dielectrics. We added a whole bunch of things to get rid of interference. Guess how we make wireless go faster? The exact same thing. We need to lower interference in wireless. And what's the number one cause of interference in wireless? Other wireless. So we have a lot more control over this than we think we do. Now, if we look on we're still over on the right side in the blue ones. If we look, and this is the fast version, I have obviously a bunch of slides on all the little pieces. We just don't have time to talk with them all. But there is, for each one of these bubbles, from the local network to DHCP to DNS to Radius to the database behind Radius, all of them could have individual issues that we have to deal with. From the ports that a Radius server is connected to an AP, and if those aren't configured properly, it's going to end up looking like a wireless problem when it's 100% wired problem. One of the big problems we come across is this. How do we tell, how do we tell, is it a wired or wireless problem? So in this example, the top little box came from speedtest.net, and I was pulling down a whopping 1 meg data rate with less than a meg of upload. I happen to be at a hotel in a place called the Silicon Oasis outside of Dubai. We have Silicon Valley, we have Silicon Slopes in Utah, we have Silicon something everywhere. In Dubai, they call it Silicon Oasis. And this was one of their prime hotels, brand spanking new in this place. And if you look down below, I was using a Wi-Fi tool from Adrian Granados on my Mac, and it shows what the AP is offering. It shows what the signal quality is, the channel I was on 80 megahertz wide channel. My laptop could do 1.3 gig, but the AP could only do 867. And so we were maxing out. I was with 41 SNR, MCS 9. Every time my client put together a frame, it used the maximum way it could. 256 QAM, 5 to 6 coding, 80 megahertz wide channel, short guard interval. It did everything it could. And so the wireless was fantastic. It could not be better with that access point. But why was I only getting a 1 meg data rate? Well, obviously I go down to the not obvious, but I did. I went down and went to the front desk and said, yeah, you have a wireless problem. And they went, what? Yeah, wireless. I said, actually, you don't have a wireless problem. You have fantastic wireless. It's working wonderful for me. What you do have is a backhaul problem. And they went, no, we just spent, hundreds of thousands updating our wireless. I said, you might have, and it worked really well. But the problem is on your backhaul. And I could tell because the client I was using was reporting to me the exact modulation it was choosing. If it had a hard time with wireless, it would have dropped. It didn't. What this is showing is I definitely had a wired problem. So what we need to do is look and say, is it a wired problem or a wireless problem? And we need to be able to do this very quickly. If it's a wired issue, I'm going to use entirely different tools to check upper layer issues. If it's a wireless issue, I need to use a different set of tools to check a wireless problem. I would love it if our end users could tell when they call up to TAC or when they call up tech support and say, my wireless is getting MCS of 7, but I'm only getting on the internet really slow and my Netflix is messed up. Well, if I have MCS of 7, I don't have a wireless problem because Netflix only needs 4 meg, maybe at HD, 2 meg at SD. So the slowest possible data rate I could pull off a wireless is 6.5 meg. So even at BPSK, the worst possible modulation, I should still be getting Netflix. So I want my end users to self-diagnose, just like we have wireless self-diagnose by telling us what their MCS index is. I would like my end user to do the same thing. They need to be able to look and say, is it a wired issue or a wired issue? So I put together a little table that will help you with that. If you have a IP address on your wireless client, you don't have a wireless problem, because the only way you got that IP address over the wireless client was over the wireless network. You had to associate, you had to authenticate, you had to encrypt, and when you're done with all of that, sorry, I was just hearing a noise there. When you were done with all of that, you then get an IP address. So obviously the wireless is working if you could even get to that part. If you can ping the client from the wired side and you can hit a wireless client, yeah, it's going over the wireless, it's working. The big one, the one I like a lot, is the MCS of the wireless client. If I know where the wireless client's MCS is, he is telling me frame by frame the health of the RF. So if it's doing 5 to 9, that means that 64 QAM or better. Now, when I design wireless, I try to keep it, I design for 64 QAM. Now, inside of 64 QAM, there's some changes. There are coding issues. And the coding issues can flop around. And depending on why those coding issues change, it tells me a little bit about the health of the RF. But if I can stay between 5 and 7, 64 QAM is great. If I'm 8 or 9, that means I'm getting 256 QAM. That's fantastic. But if I'm between 5 and 7, I'm great. If the spatial streams are jumping around, that is an environmental issue. I can't change that. There's nothing I can do in the physical environment that's going to change the spatial streams. Well, one, I could put the APs in the proper location, but there's nothing I can do remotely that's going to fix that. Now, if I have MCS less than 5, that's the client self-reporting, I'm having issues with RF. Now, mine only dropped down from 64 QAM to 16 QAM and still doing a pretty decent thing, but it's at 16 QAM because it has an issue. The issue could have been because of contention, the issue could have been because of ACI or CCI, the issue could have been because bad SNR, lower RSSI, I don't know, but it's also consistent. When it drops down to 1 or 2, we're having a real issue in the RF. So I can just use that alone to track that. Now, if I don't have tools to look at it from the client standpoint, I can log into the controller, and the controller will report what it transmits downstream, its MCS, its data rate, and some controllers will also report back upstream. If you're running SevenSignal Sapphire, you can get into the Sapphire the dashboard and pull the same information. It's gleaming it from the air. If you're running Mobileye on your device, you'll be able to get the same information from Mobileye. The other one I like to do is compare throughputs. I compare a Wi-Fi connection data to an internet speed test, just like I showed on the previous slide. When I connect up and I've got a high MCS and I'm pushing data at 866 to the AP, but the AP is only giving me back 1 meg, that's a wired issue. So I can quickly tell, is it a wireless issue or wired? Now, I can't do that in reverse. If I am having a poor time in the air, and then I will obviously get a poor internet connection. So I can't tell that if I have bad Wi-Fi that I have bad backhaul. But if I have good Wi-Fi, I can always tell if there's bad backhaul. So just using these quick tests. The RSSI and SNR, both from the client's point of view and the access point's point of view, is going to tell me a lot about the health of the network. And the last question here is it isolated? Does it happen only on Wi-Fi? I get people like, oh yeah, we've got this terrible problem, and it's a DNS problem. But the Wi-Fi users complain. I said, well, is it also on the wired? They went, oh, we don't know. We don't have any wired clients anymore. So a lot of times, anything that happens wrong in the wired side is going to look like a wireless problem. Okay, so that's my presentation about the things, and we ended with this little quick question. which means it's time for a Q&A. And
Yes,
that's all I have. But if you want to get any of the resources, I have a URL you can have on the screen, and you can get any of the graphics that I've used today. And let's have questions. Jim?
Yeah, thank you very much, Keith. And Jim, want to bring you into the picture here. We do have some questions. And you know, it's funny that you mentioned the graphics, because one of the questions, Keith, was where can I get the laptop graphic with the PCM CIA card? So I think we just
that one isn't on this website.
That's a classic.
Definitely a classic.
All right, so let's start with some questions here. They're just all over the place. Jim, we'll let you answer these questions, and then obviously Keith, if you'd like to add additional color, let's do that. So one of the questions was with regards to the contention process that Keith was talking about, and the question was, won't the 802.11ax new standard solve this issue of the contention process?
Yeah, so you could give a 45-minute answer to that, or just a quick nugget, but it will change it significantly, certainly, and it will make it more efficient in the best case scenario. At the same time, that process you're looking at right now, it still is in play for OFDMA, which is the new protocol that allows for a simultaneous transmission of frames to multiple stations at once. The AP still has to gain control of the channel through this exact process you're looking at. Mm-hmm. And so one of the issues you'll see is that if you're running 802.11ax in the 5 gigahertz band, and you've got a lot of, we'll call them legacy clients, so that's 802.11ac or previous generation clients, the AP has to contend for the medium with them whenever it wants to do that neat OFDMA trick. And before I go too far down the rabbit hole, I'll stop there and let Keith answer as well.
Yeah, I think the AX promise of fixing this isn't going to happen for a long time, because until you have a predominance of AX capable clients, the RF airtime still has to be shared the same way that's always been shared, and it's backward compatible. Now, on the positive side, when we get 6 gigahertz available to us via the FCC, 802.11ax or Wi-Fi 6 in 6 gigahertz will be the only technique that can be used with no backward compatibility. So that means in 6 gigahertz, we won't have this problem. So the quick answer to your question is 6 gigahertz. Yep, I think we're going to solve this somewhat. There still has to be a transmit opportunity that's been negotiated, and that takes time, but it's more efficient than we have currently. But in 5 gigahertz and 2.4, which are both AX capable, the legacy clients are going to be driving it, and until we have some ratio that's above 60-80%, the effects are going to be minimal.
You know, Keith, the other thing to talk about here is BSS coloring. I think OFDMA gets a lot of attention, but BSS coloring is a new feature that'll affect the contention process as well. And essentially, what that's going to do is it's going to let clients that are joined to different APs that are operating on the same channel be, how should we say, less sensitive to each other. So there's a greater probability that they'll transmit at the same time if there's enough SNR between them. So that can, it will have an effect on CCI. It's not a cure for CCI, but it will potentially improve things.
I'm a little afraid when people get into BSS coloring and they think that it might fix CCI. Good design fixes CCI.
Yeah, I have the same concern.
I don't want people to get lazy and have just a whole bunch. And they're like, it'll fix it all by itself. No, it's a partial solution. Good design and having no CCI will make BSS coloring not needed.
Yeah, I'm afraid it might be something you can really shoot yourself in the foot with too. If you've got APs really close on the same channel, but they're using different colors, they're still going to stomp all over each other. It doesn't, I mean, those frames aren't going to be able to be demodulated, so it's something you have to use with care.
It's a neat trick. So next question.
Okay, awesome stuff, guys. So one question was with regards to the ground differential between AP and switch. And the question is with regards to, does the Cisco access point have a ground?
So this, I found this only in outdoor APs when they have a grounding lug. If you attach the grounding lug outdoors to the building ground, and yet the Ethernet port is connected and it's sharing ground with the switch, which may be on a different ground, that grounding differential will bear that the Ethernet won't go at full speed. Indoors, you're all sharing the same ground and you don't use a grounding lug on an indoor AP, its ground comes off of the Ethernet port. So then they're shared.
Okay, very good, very good. Okay, Jim, where have you used or seen the use of Mobileye to monitor and identify wireless LAN network problems for, where those problems are for the IP staff, for airports, hospitals, stadiums? Can you shed some light on your experience there?
Yeah, so sure. So some of our biggest verticals are folks that have really mission critical Wi-Fi networks. So that's hospitals where everything's wireless, and it's medical equipment using the Wi-Fi network depending on it. That's manufacturing, where they typically can quantify exactly how much it costs them for every minute of network downtime. And then higher education, another big vertical for us, right? Everybody's using Wi-Fi in lecture halls, and apps are in the cloud, and we need visibility. And then all wireless offices are a really growing segment for us. One way to save cost when you're building a new office is to bring your switch port down by only providing switch ports for APs, and then requiring everyone, even people that aren't moving around, to use the Wi-Fi.
Right. So Jim, how is Mobileye going to help in those situations?
Yeah. So Mobileye, you can think of it as turning your computer, your endpoint, into a sensor. So it's going to run tests from the client device and collect all the test results and client information that you need to make judgments about troubleshooting issues. So we're going to collect the RSSI over time, the channel it's connected to, the AP it's connected to, the data rates that it has been using. So if you see those data rates go down during a period where a user said there was an issue, like we learned from Keith, that indicates there was an RF problem. It also does active testing. So ping tests, throughput tests, VoIP tests, simulated voice call, and calculate a MOS score, so that you can tell if your applications are working and if the infrastructure can deliver the performance that's required by your design. So it's a very thorough tool. You also can learn a lot about the endpoints themselves. You can get an inventory of the adapters, the wireless adapters, and the driver versions that they're running. And that's always an eye-opener for our customers, because very few people have any idea what driver versions they've got. It's usually whatever came out of the box, and
right.
Upgrades often can help remediate issues on those clients.
Yep, I hear you. Okay, Jim, anything specific on the correct physical position of APs when you're installing access points? Any advice on how they should be physically positioned, I guess, to read into the question a little?
Sure. All the major manufacturers, and not to punt on this, but they all have design and deployment guides that make pretty clear how each specific model should be deployed. But in general, an omnidirectional AP with internal antennas, indoor AP, your typical AP that you see, should go on the ceiling, should be close to where the bulk of your users are. That's kind of a good heuristic, at least.
Okay, fantastic. All right, so one of the things that Keith mentioned early in his presentation was the phrase "my S is your R." This idea of, you know, the wireless interfering with wireless. So the question is, if I use ARM, which is a form of radio resource management, isn't this designed to solve those problems? What's your take on that, Jim?
It is, but you know, if it worked really, really well, and it's not this isn't a knock on Aruba, it's everybody's auto channel or auto RF algorithm. If it worked really, really well, there wouldn't be a Keith Parsons or a Jim Vada or all these other CWNEs that are so busy, you know, untangling the mess that it makes. So it's supposed to do that. My experience is in the real world, it falls apart pretty easily. Keith, you want to add any color to that one?
I think it fits in the, what do you get paid for? So I get paid for fixing bad Wi-Fi, and one of the first things I do is turn off RM and fix it statically. So I have years, decades of experience making RM or ARM or whichever, the automatic ones, better by using my technique. I'm just flat out saying I get paid for that, so that's my view of the world. Vendors who sell hardware don't get paid for work I do, so they push their automatic system because it's part of the CapEx that the end users buy. Everyone gets paid for doing whatever they do. If it worked, I wouldn't get paid. My solution works, but it's really expensive and it's hard to repeat. So there's a reason why the automatic ones, you know, you have a hospital of 2,000 APs. You're like, you're going to set those static? No, I even use RM. I turn it on, let it run, settle down, lock it, survey to find out the couple of problems, and maybe only have to fix 20 or 30 out of the 2,000 APs that RM made a mistake on. So those people who are really, really good at RM can make a really useful tool. You just have to know how to do all its little tweaking. There's like, I don't know, I think it's a 137-page document just on how to tune RM. If you use them out of the box and just set it as defaults, yeah, you're going to have issues. But if you tune them properly, you can get them to work really good. So I'm not anti-RM. I'm just admitting my bias is because that's how I get paid.
Very nice. And we all need to make a living, don't we, Keith? So here's the next question. And Keith, you know, this might be one for you also. Somebody had indicated that there was a rumor that MacBooks were going to be coming out with, or they were going to be 5G capable. Now, if that's the case, if MacBooks are going to move towards being 5G capable, then, you know, what is this? How does this change the Wi-Fi landscape moving forward? Any thoughts on that topic of 5G versus Wi-Fi?
Sure, lots of topics. The idea of 5G beating Wi-Fi or competing with Wi-Fi, I think is a little almost hilarious. 5G requires Wi-Fi in order to do its job. It's designed specifically when you're using the millimeter wave, they don't travel inside of a building. So the 5G infrastructure is designed to use Wi-Fi indoor and cellular outdoor. The other side of it is cellular will always be about something called ARPU, A-R-P-U, the average revenue per user. They want to make their money on the traffic flow. Wi-Fi, on the other hand, is about we put in infrastructure and then the traffic flow is free. So there will continually and forever be a difference between how cellular world sees data flow and how Wi-Fi, and we work together. So I don't think it's either or. I also don't know. I don't believe that rumor.
All right.
It may be true, and if it is, great. If not, we'll still be using Wi-Fi because it's free.
That is true. All right, I think we have time for one last question. Jim, what is the RSSI threshold for the BSS coloring to work that you were talking about before? Or two overlapping channels, APs, side by side can work without having to contend? Does that make sense?
Yeah, so so the standard, so that there isn't a clear answer to that. The standard defines.
I'm looking forward to your answer.
Yeah, that's a tough one to finish up with. The standard, the 802.11 standard says and Keith, tell me if I'm wrong, but you need minus 82 dBm or minus 85 dBm to trip that that the channel is busy from virtual carrier sense, where you've demodulated a frame from another station. And so what
I
BSS
think it's actually, it's 4 dB above the noise floor.
Yeah, so right, and so
depending on the noise floor, it could move, but it's still out there.
Correct. And so what BSS coloring does is it just changes that value for frames that are transmitted with a different color. So that sounds simple enough. Maybe it changes to minus 65. I don't know if that's standardized in 802.11ax or not. But the wrinkle I would add is that even though the standard says it's 4 dB above the noise floor, the actual behavior of 802.11 radios is unique and complex, and some are much more sensitive than others, and so they will back off and not transmit in the face of very, very faint signals, and some are far less sensitive and transmit over top of other frames very readily. So yeah, that's sort of my quick take on it.
All right, that's good. And you know what? I'm going to go into overtime here in order to throw out in order to end on a great note with a real positive question. So one that just came in was with regards to trying to find wireless LAN professionals in my area. What groups should I use, or certifications or groups should I use to find Wi-Fi professionals in my area? Now, this question is specific to Vancouver, Canada, but do you guys know, or do you guys have, Keith, do you have any advice on how to hook up with people in your local area, whether it be locally, meetups, LinkedIn, whatever it might be?
So first, I would say get on Twitter. There's a massive amount of traffic on Twitter. There's also a Wireless LAN Professional Slack channel. Sam Clements or Manon Lassard are kind of gatekeepers for that, and you can see both of them on my website. You can see that there is a blog roles, both on my website and a whole bunch of other people's websites. So you can check blog roles, you can check Twitter roles. There are people all over. There's also activities that are local. There's a Wireless LAN Association that has local chapters. So Wireless LAN Association is WLA.org. You can check that one out. In Vancouver, I know of 3 or 4 people that would love to get engaged and meet for dinner or lunch and talk Wi-Fi. There's a bunch of those ad hoc ones going on just about everywhere. So if you're in one and there's not one, you start one. So yeah, if you want to start one in Vancouver, I can link you up. If you hit my web page I'll put it on the screen here, just the WLANpros.com. There's Twitter roles, blog roles, other web pages to hit. Go enjoy. There's lots of activity in the community.
Awesome. Isn't that the truth? You know, we are a tight-knit group who enjoy helping one another. And Keith, we are certainly privileged to have you helping us today. So that's going to conclude our presentation. Keith, I want to thank you on behalf of SevenSignal for joining us today. Jim, want to thank you as well for stepping into the hot seat and answering some of those tough questions. And this presentation will be made available. Be on the lookout for that email that allows you to download or view the presentation online. And with that said, I'm going to wrap things up. And Keith or Jim, any parting words?
Nothing here, thanst.
Yeah, you bet.
Yeah, thank you.
Keith, thank you. And it's our pleasure. And everybody out there, have a wonderful rest of your day, and be on the lookout for more incredible content coming your way. Thank you kindly.